Good day, everyone. Today, our presentation is about numerical methods for solving differential equation with a focus on Euler's method. So, differential equations are widely used to model real life phenomena such as population growth, heat transfer, fluid flow, and drug concentration in the human body. However, many differential equations cannot be solved analytically using exact methods. Therefore, numerical methods are used to approximate solutions when exact solutions are difficult or impossible to obtain. One of the most basic and commonly used numerical techniques is Euler's method. So in this presentation, we apply Euler's method to a drug elimination model, which describes how the concentration of a drug in the blood changes over time after injection.
Okay, now let's see our programming software, which is Microsoft Excel. When we think of programming, we usually think of writing lines of code in a text editor. However, Excel is a powerful reactive programming environment. In Excel, every cell acts as a memory variable, and every formula is a logical function. For numerical methods like Euler's, Excel is ideal because its grid-based structure perfectly matches the step-by-step nature of solving differential equations. The coding in Excel relies in cell referencing. To program the Euler methods, we use relative references for the previous concentration, allowing the calculation to move forward in time. We use the absolute references for the constant, like the elimination rate of K. This ensures that we loop our calculation down the road. Our mathematical constant remain fixed while our variable update dynamically. One of the biggest programming in Excel is reactivity. In a standard script, you must rerun the code to see the change. In Excel, the engine is always live. If we change the value of k in input cells, the change ripple through every row of Euler calculation and update the graph instantly. This makes a superior tool of what-if analysis in medical dosing. Why we use Microsoft Excel instead of another software? The first one is ubiquity and access graphic, which icons representing different industries like finance, medical, engineering, which are connected by Excel logo. And the second one is a transparency program. An image showing a Python code flag where math is hidden versus an Excel spreadsheet where every row is a visible math step. The third one is the low barrier scale, a scale showing high complexity and steep learning curve in Python or MATLAB versus immediate productivity in Microsoft Excel. Next, what is an educational value and rapid prototyping in Microsoft Excel? Beyond calculation, Excel is a powerful tool for education and rapid prototyping. In education, Excel provides a mathematical transparency. Unlike other software where code is hidden, Excel shows every intermediate step. This helps students visualize, especially how Euler's method works row by row. For prototyping, Excel is a no-code sandbox. We can instantly test what-if scenarios like changing a dose or patient's clearance rate and see the graph update in real time without rerunning any scripts. This makes it a perfect tool for building a quick interactive proof of concept.
Okay, next, I will present a numerical solution for a differential equation using Euler's method. Okay, first of all, we need to know that Euler's method is a numerical technique that is used to approximate the solution of differential equations when an exact solution is difficult or impossible to obtain. So in this assignment, we use the following differential equation model, which is dc over dt equal to negative kc, where Ct represent the drug concentration in the blood, T is time, and K is the elimination rate constant. So this model shows that the drug concentration decrease at a time proportional to its current concentration. Okay. Now to solve this differential equation numerically, we choose Euler's method formula, which is Cn plus 1 equal to Cn plus H in bracket negative K Cn, where Cn is the current drug concentration, H is step size, and Cn plus 1 is net drug concentration. Okay, now let's see the scenario of drug elimination after injection. So the given information from that situation we get is initial drug concentration C0, elimination rate constant K equal to 0.2 hour times step size H equal to 0.5 hours, and differential equations which is dc over dt equal to negative zero point 0.2 C. So using these values, Euler's method is used to estimate the drug concentration in the bloodstream after 3 hours. So the problem we want to answer is, how does the drug concentration in the blood change over the first 3 hours after the injection? So by applying Euler's method, the drug concentration can be estimated step by step at fixed time intervals. So this numerical approach can help doctors and pharmacists estimate drug level in the body and support safe and effective drug usage. Next, I will pass to my friends to continue present about coding for numerical solution.
This slide shows the numerical solution for a drug concentration problem using Euler's method. In this situation, a drug is injected into a patient with an initial concentration of 50 mg per liter, and it is eliminated from the body at a rate proportional to its concentration with an elimination constant of 0.2 per hour. This process is modeled by the first order differential equation dc over dt equal to negative 0.2 C. To estimate the drug concentration after 3 hours, Euler's method is applied with a step size of 0.5 hours. The Euler formula used is Cn plus 1 equal to Cn plus H bracket negative Kcn. Using this formula, the concentration is calculated step by step starting from the initial value. The table shown represents the coding and calculation in Excel, where the concentration decreases at each time step as the drug is eliminated from the body. At time, which is t equal to 3 hours, Euler's method estimates the drug concentration to be approximately 36.57 mg per liter. This numerical result provides a practical approximation of the drug's behavior over time. The graph shows that the drug concentration decreases over time, indicating a declining trend. This downward curve reflects the elimination of the drug from the bloodstream. The Euler method graph follows this decreasing pattern, showing that as time increases, the estimated concentration becomes lower at each step. This behavior is consistent with the nature of the differential equation, which models exponential decay. The slide shows the exact solution of the differential equation modeling drug concentration in the bloodstream. The process is described by the first order equation dc over dt equal to negative 0.2 C with initial condition C0 equal to 50 mg per liter. By separating variables and integrating, the exact solution is obtained as Ct equal to 50 exponent of negative 0.2 T. Substituting T of T equal to 3 hours gives a concentration of approximately 27.44 mg per liter. This value is slightly higher than the Euler method result because the exact solution represents the true continuous behavior of the system. When comparing the graph, the exact solution forms a smooth and continuous exponential decay curve, which represents the true behavior of the system. Meanwhile, the Euler method is constructed using step-by-step linear approximations. Although Euler's method is theoretically piecewise linear, the graph appears slightly curved because many small linear steps are connected together, especially when a small step size is used. As a result, the Euler graph lies slightly below the exact solution, indicating that Euler's method slightly underestimates the concentration.
In conclusion, the assignment demonstrated how the drug concentration problem can be solved using numerical methods, specifically the Euler method. So by applying this method in the Excel, we were able to approximate the changes in drug concentration over time effectively. So the Euler method will approximate the solution of differential equations with when an exact solution is difficult to obtain. So why we choose Excel compared to other programming software is because it's ubiquity and access graphic, the transparency diagram, and the low barrier scale. So the problem that we choose in our assignments is the way how the drug concentration in the bloodstream change over the first 3 hours after the injection. So in this assignment, the Euler method will estimate the drug concentration in the bloodstream after 3 hours and with a step size of H that equal to 0.5 hours. So basically, the Euler method provides a simple and reliable approach for estimating solutions to real-life differential equations problem. As in our case that we choose is drug concentration problem. That's all for our assignments. Bye. Thank you for watching.